what we were talking about last class, we weren't able to get all the way through the geometric model, but we had talked in depth pretty much about our assumptions and conditions, what we needed to use the geometric model. What was the first thing we needed for the geometric model? In order to use the geometric model, what do we need? Has to be binary. Yes, got to have binary, which means success and failure, yes or no. Okay? Then we had what? Independence. That meant the probability of one event occurring should not affect the probability the next one should occur. And that kind of ties back into the S, which was success. Probability of success needs to be the same. Independent maintains the same probability. Okay? And then the last thing makes it geometric. What was that? Trials. Where it's one of those go until. Okay? And then I pulled up these formulas for you guys. And it looks a little weird. But basically, what this indicates here is it says the probability out of all of your outcomes of it taking this many, this lowercase x trials to get a success, we're going to have failures until a success. So that means if it takes me 5 times to make a success, I had 4 failures before that 5th time. And we can find the expected value by just taking 1 over the probability. And the standard deviation, which we're not going to use all that much here, is the root of q over p squared. Just formulas you got to know. Okay? So, did we get to do this problem last class? Yeah? So, if we're saying the probability that the 5th chip you test is the first bad one you find, you got to be careful with how you define success and failure for this. I would say success is the 5th chip you test is the first bad one you find. So I'm looking for the bad one to be my probability of success. So basically I'm saying, okay, good, bad. Right? So that means it's going to be 0.98 to the 4th times 0.02. Now, what we were talking about before class ended is we were kind of briefly going over our calculator commands. And so let's kind of go over that one more time. What we were saying on this is we are right now talking about the geometric distribution. And if you go to your second vars, all the way at the end, there is your geometric. PDF stands for one specific outcome. Okay? That's what we were talking about here, where we're saying, okay, what is the probability the 5th chip you test is the first bad one you find? Well, the probability of getting that bad one is 0.2. So I'd go to my calculator, and I'd say I'm just doing one possible. Probability is 0.02. I want it to occur on the 5th one. And there it goes. It'll do the math for you. Okay? The next question says, what is the probability that you find a bad one within the first 10? That means it could happen as soon as which try? The first one. Could happen on the 2nd, the 3rd, the 4th, the 5th. It's just going to keep going. All the way up to the 10th one. Now that is way too many probabilities. You could sit there if you wanted to, and you could physically calculate out, the pen that I know is going to show up, the probability that the first fail is on the first one, probability that the first fail is on the second one, probability that the first fail is on the third one, and on and on and on until you get to the 10th shot. But that is just way too much. So instead, I know that I'm doing a geometric model where the probability for success is 0.02, and I've got some number of terms, and I want to find the probability that it happens within the first 10. if you show me this, that's enough work to then go to your calculator. I'm just going to write this down and to do geometric CDF. And this chapter, guys, this one unit is the one place where showing me your calc speak is good enough. So I'm going to go to geometric CDF. Let's just look to see what it prompts. Geometric CDF says P. So I'm going to write down what my probability of success is. X value, that means I'm going through the 10th position. Close my parentheses, hit my stuff, hit enter, and there's my answer. Okay? This is good enough for me. Can you let Sal back in? Does that make sense to you guys? I want to see CDF or PDF. Each one of these is a PDF. You see probability of success and when are you going till. Okay? All right. Or you could have written it all out on your calculator and that's just a pain in the neck. Okay? All right. So using the same thing. If I now ask questions like, how many do you expect to test before finding a bad one? What am I looking for? If we just kind of think about the language that I'm using here, I'm asking you to find expected value. You know what I'm talking about? Because it says, what should you expect? What is another word for expected value? Mean. What's another word for expected value? What? Average. I'm just kind of like, what are all these different words that you could say? What should you expect to occur? What should the average outcome be? What is the mean of all of your outcomes? How do you calculate expected value with a geometric model? 1 over P. Yeah, 1 over P. So in this case, what was P? 0.02. So to figure out how many I should expect, it is just 1 over 0.02. So that means I should expect to find a bad chip within the first 50. That doesn't mean I'm going to be awesome on 49 in a row and then on the 50th one it's going to be bad. It just says that, you know what, usually over an extremely long run, you kind of expect to find a bad one within the first 50. Okay, somewhere within there. I don't care if it's the first, the last, the middle, whatever. Does that make sense, though? Are we okay? All right. Okay. Let's go ahead and read through this. A lot going on in here. We're kind of combining some of our rules. Okay, ready to kind of work this through? All right, so we're looking for here, for what? What am I asking you to find? Expected count, expected value, however you want to say it. So I have 20% of folks donate, 5% of my donators give more than $100 or $100. I want to find how many should we expect to get somebody who gives $100 or more dollars? What do you need to do first here? Why? Exactly. It's like it is a conditional probability. The first thing you've got is, did they donate, yes or no? And then, did they give more than 100? Yes or no? Or you can think the probability that you got a donator who gave $100 starts off with the probability that they donated times the probability that they gave the $100 given that they were a donator. So that's 0.2 times 0.05. What is that? 0.01. So this is my P. This is the P that I'm talking about. How do I figure out how many people they should expect to call until they get somebody who donates? Right. So we're going to say the expected value is 1 over P. So how many people? 100. Now, the question here said, on average, how many potential donors will she have to contact until she gets her first $100 donor? What do I need to make sure that I do? Put it in context. I know it's your favorite thing in this class, right? No, it's not. You all hate this. So for the context, what I'd have to do is I'd go through, I find the 100 contacts, but the way that you phrase this is really important, is we expect she will have to contact 100 potential donors to get a $100 donor. That doesn't mean the 100th person is going to be the donor. It just means within that, I just be all over you. Within that, we should be able to find someone. As I stand blocking Brandon's view. Okay, is it kind of coming together a little bit better today? You know, now that we've actually had time to look at a problem or two. Sometimes that helps. Okay? I want you guys to do this problem. A and B both.
So that's your P, right?
No. So it's 1 minus